Welcome to Brain Vision.
So for this question, we're looking at the example in the textbook 8.8, right, at part B, where we have our block already compressed against a spring, right, up to a compression of 0.0924 meters, right. So this is the compression in the spring. And we know that in order for the block to go back to the unstressed position, it would have to overcome friction using the amount of elastic potential energy that is stored in this spring, right, to overcome the frictional force. And we're given that the friction is 3.92 newtons, right. So therefore the total work done in order for it to push it back to the original position would be F times X, which is 3.92 times 0.0924. This is about 0.362 joules. So this is the amount of energy that is required to work against the friction in order to go back to its unstretched, uncompressed position. But the amount of elastic potential energy that is stored over here, which is half kx squared, is just equals to half. The k, the spring constant, is given as 50 newtons per meter, and the x is 0.0924 square. So this is only 0.214 joules, right, which is less than 0.362 joules. And because it's less than the amount of energy required, therefore it cannot push the object back to the original position at x equals to 0. So for the next part of this question, we want to find what is the coefficient of friction, mu k, that will allow the block to actually move back to its original position. Now we are given that at the start the block approaches the spring with a velocity of 1.2 meters per second. So the total kinetic energy, half mv squared, is given as half 0.8 times 1.2 square. It's about 0.576 joules. We know that it will travel against the friction, right, as it compresses and also as it relaxes. Right, at this frictional force, the total work done by this frictional force will be F times 2x. This is a total work done by friction. And for the block to just be able to go back to its original position, it would mean that this total work done must be the total kinetic energy that it has at the start. And therefore we can actually find from here what is the total amount of work done. So F times X is about 0.288. Right, so this is the total work done by friction, and also this is only for when it just compresses. So this is so equated to the overall elastic potential energy that is stored in the spring. Right, and with this we can actually calculate what is our x, which is just 2 times 0.288 divided by k, then we take the square root. So give us about 0.107 meters. With this, we can find what is our frictional force, F. Frictional force would be just 0.288 divided by this answer, which is about 2.68 newtons. And this frictional force is given as mu k times the normal force. And the normal force is dependent on the weight of our block. Right? So we can get mu k by simply dividing the force by the weight, mg. This gives us 0.342. Therefore, this is the coefficient of kinetic friction that is needed for the block to go back to its original position.